Welcome to DAR Tutors for online and home tuition. In today's lesson, we will be focusing on Spearman's rank correlation coefficient, a key concept in IB mathematics, applications and interpretation higher level. By the end of this session, you will be able to, first, find and assign ranks to bivariate data. Second, calculate Spearman's rank correlation coefficient. And third, use this coefficient to describe and interpret the relationship between two variables, especially when the relationship is not perfectly linear. Let's begin. We often use the Pearson's product moment correlation coefficient, or RP, to measure the strength of a linear relationship. But what if the relationship isn't linear? Consider the relationship between a person's age and their height. In childhood, height increases rapidly. Then it slows down significantly in adulthood, eventually plateauing. While there is a clear positive trend, this relationship is not linear. In cases like this, where the association is clearly not linear, using RP can be misleading. This is where Spearman's rank correlation coefficient, denoted RAMACS, becomes a valuable tool. Instead of looking at the data values themselves, RS measures the strength and direction of a monotonic relationship between two ranked variables. A monotonic relationship is one that is always increasing or always decreasing, but not necessarily at a constant rate. In essence, Spearman's coefficient tells us how well a relationship can be described using a monotonic function. Let's work through our first example to see how to calculate and interpret Spearman's coefficient. We'll start with a straightforward case without any ties. Suppose a research team wants to study whether the number of times a person exercises per week is related to their score on a standardized fitness test. They collect the following data from 7 participants. Here's the data. For participant A, we have 2 exercise sessions and a test score of 12. For B, 4 sessions and a score of 18, and so on. Our goal is to determine the Spearman's rank correlation coefficient for this data. The first step is to assign ranks to each set of variables. We will create 2 new columns for rank of X and rank of Y. We'll assign the rank of 1 to the smallest value and the highest rank to the largest value. For the exercise data, the smallest value is 1, so it gets a rank of 1. The next smallest is 2, getting rank 2, and the largest is 7, getting rank 7. We do the same for the test scores. The smallest score is 10, rank 1, and the largest is 4, rank 7. Now that we have the ranks, calculating RS is simply calculating Pearson's RP on these new ranked variables. Many calculators can do this, but if we wanted to calculate it by hand, we would use a simpler formula. This is the formula for Spearman's rank correlation coefficient. Let's break down this formula. N is the number of data pairs, which is 7 in our case. D is the difference between the ranks for each participant, and SD2 means the sum of the squares of these differences. Let's create a new column, D, by subtracting the rank of X from the rank of Y. Then we'll square each difference to get D2. As you can see, the differences D are all 0 because the ranks are in perfect agreement. This is a special case. Now we sum the D2 column. The sum is 0. Plugging this into our formula gives us RCU ISIS equal to 1. This result, 1, indicates a perfect positive rank correlation. It means that as one variable increases, the other also increases perfectly, and there are no inversions in the ranks. In our example, the participant with the highest number of exercise sessions also had the highest test score, and so on for all participants. In this perfect case, RP would also be 1. However, Spearman's RS works just as well for linear relationships and, as we'll see, is superior for nonlinear ones. A common issue in rank correlation is the presence of ties, when 2 or more data points have the same value for a variable. Let's look at this example. We have 2 data points with X values of 60 and 60. These are tied. For the Y values, we have 40, 40, and 40. This is a 3-way tie. When calculating ranks, we must assign a consistent rank to these tied values. The rule for handling tied ranks is to find the average of the ranks they would have received if they were not tied. Let's rank the X values first. 60, 60, 65, 70, 75, 80, 85. The value 60 is the first and second smallest. It would have received ranks 1 and 2. We average these 1 plus 2, 2 sets 1.5. So both 60s get a rank of 1.5. This uses up ranks 1 and 2. Now for the Y values, 40, 40, 45, 60, 70, 80. The value 40 is the first, second, and third smallest. It would have received ranks 1, 2, and 3. We average these. 1 plus 2 plus 3, 3 equals 2. So all three 40s get a rank of 2. This uses up ranks 1, 2, and 3. The formula we used previously works perfectly fine even with tied ranks. You simply use the average ranks in your calculation for D and SD2. There is no need for a separate formula. Now let's work through a full example that illustrates why Spearman's rank correlation coefficient is so valuable for nonlinear relationships. This is similar to example 7 in your textbook. The population of a species of bears on a particular island is recorded every 5 years, starting from 1978. We have 9 data points. The first variable, t, represents the number of years since 1978. The second variable, p, is the bear population. Notice the population starts low, increases, and then seems to level off and fluctuate. This is a common pattern in population growth. Let's follow the steps to analyze this data. First, we'll plot a scatter diagram. Looking at this graph, the relationship is clearly not a straight line. Pearson's RP for this data is approximately 0.860, which suggests a strong positive correlation, but doesn't capture the curve. Because the relationship is nonlinear, we should use Spearman's RS. Next, we find the ranks for T and P. For time, T, the values are already in ascending order, so the ranks are 1 through 9. For population P, we rank them from smallest to largest. The lowest population is 1030, rank 1. The next is 1836, rank 2, and so on. Notice that the population values for T25, T30C, T35, and T40 are very close. 3501, 3479, 3418, and 3511. When we rank these, T35 has population 3418, which is rank 6. T30C has 3479, which is rank 7. T25 has 3501, rank 8, and T40 has 3511, rank 9. Here is the complete table with all the ranks. Now let's create a scatter diagram of these ranks. This is the scatter diagram for the ranks. Compared to the original data, this plot shows a much clearer, stronger linear trend. This confirms that a linear model for the ranks is appropriate, which means Spearman's coefficient will be a much better measure of association than Pearson's. Let's use our formula to calculate RS. First, we calculate the differences D and their squares, D2. For the first point, D equals 1 equals 0. For the second, D equals 2 to 2 equals 0. We continue this for all 9 points. Notice the largest differences occur where the raw population data started to level off or fluctuate. The sum of the squared differences, SD2, is 8. Now we can substitute this into the formula. We have SED2 equals 8 and N equals 9. Plugging these in, we get RS equals 1 minus the fraction 6 times D all over 9 times the quantity 9 squared minus 1. This simplifies to 1 minus 48 over 720, which is 1 minus 0.0667, giving us a final RS of approximately 0.93. This value of 0.933 is very close to 1, indicating a very strong positive correlation between the ranks of time and bear population. This is a much more accurate description of the underlying trend than the Pearson coefficient of 0.860, as it correctly accounts for the nonlinear nature of the data. Now let's explore some IB-style practice questions to solidify your understanding. Question 1 asks for the correct matching between real data scatter diagrams and their corresponding rank diagrams. Diagram A shows a strong negative association that flattens out, which is nonlinear. Diagram B shows a strong S-curve, also nonlinear. Diagram C shows points scattered with no clear pattern. Let's analyze them one by one. Diagram C, with no clear pattern, would likely have a rank diagram that also shows a lack of a strong trend. This would correspond to a Spearman coefficient near 0, or a rank diagram with no clear pattern like Diagram A. We can rule out the perfectly linear one. Diagram A has a very steep negative trend that flattens. This is a strong monotonic relationship. When ranked, this should produce a very strong negative linear trend. This matches rank Diagram B. Diagram B has a strong positive S-curve. This is also a strong monotonic relationship. When ranked, this should produce a very strong positive linear trend. This matches rank diagram C. Therefore, the matches are A to B, B to C, and C to A. Here's our second question. It's a two-part question about Spearman's correlation coefficient. For part A, remember that a negative correlation coefficient indicates a negative trend. As one variable increases, the other tends to decrease. Since RS is negative, the trend is negative. For part B, the answer is no. We cannot determine linearity from RS alone. A high RSS value simply means the relationship is a strong monotonic one. It could be linear, or it could be a strong curve. To determine if it's linear, we would need to look at the scatter diagram. Our third question examines the effect of outliers on correlation coefficients. Let's begin by plotting the data on a scatter diagram. The scatter diagram shows a clear outlier. The point, D1-35, is far removed from the rest of the data. This point represents a day with a high temperature but very few customers. We can see that for the other 12 points, there appears to be a strong positive relationship. First, let's use a calculator to find the coefficients with the outlier included. We find Pearson's RP is approximately 0.449 and Spearman's RS is approximately 0.701. Now we remove the outlier, 31, 35, and recalculate the coefficients for the remaining 12 data points. After removing the outlier, we recalculate the coefficients. Pearson's RP jumps from 0.449 to 0.900, a massive increase. Spearman's RS also increases from 0.701 to 0.941, but the change is less dramatic. Comparing these results, it's clear that Pearson's RP was much more affected by the presence of the outlier. This is a crucial takeaway. Because RP uses the raw data values in its calculation, it is highly sensitive to outliers. Spearman's RCS, on the other hand, is calculated from the ranks, making it more robust and less susceptible to the distorting influence of extreme data points. Therefore, when you suspect outliers are present, Spearman's coefficient can provide a more reliable measure of the overall trend in the data. Question 4 looks at the relationship between the time taken to fold a paper crane and the number of cranes made in an hour. Before we calculate, let's think. If it takes you longer to fold a crane, you'd expect to make fewer cranes in the same amount of time. So we anticipate a negative correlation. Let's plot the scatter diagram. It shows a decreasing trend, but with some scatter. This confirms our expectation of a negative correlation. First, we'll calculate Pearson's RP using a GDC. For this dataset, Pearson's RAP is approximately negative 0.749. Now, let's find the ranks and then calculate Spearman's RS. We find the ranks for both variables. Note that there are no ties in this dataset. We then calculate the differences D and the sum of D squared, which is 108. Using the Spearman's formula with N ma 8 and SD2 so 108, we get RS equals 1 minus 6 times 108 over 8 times 8 squared minus 1. This gives us approximately negative 0.929. Wait, I seem to have made a mistake. The question asks to calculate RS. Let's recheck the ranks and the calculation for RS to ensure accuracy. This is a good lesson. Always double-check your work, especially with tedious calculations. My apologies. I made an error. Let's restart the Spearman's calculation carefully. First, the ranks for T, 4, 1, 5, 2, 6, 3, 6.5, 4, 7.5, 5, 8, 6, 9.5, 7, 11, 8. These are correct. Now the ranks for C, 4, 1, 5, 2, 6, 3, 7, 4, 8, 5, 9, 6, 11, 7, 16, 8. No, that's not right. Cranes made is what we want to rank, and 7 appears twice. Let's re-rank C. Okay, the correct ranks for C are 1, 2, 3, 4.5, 4.5, 6, 7, 8. Now let's recalculate the differences D and the sum of D squared. We get a sum of 27.5. Now, plugging SD2 equals 27.5 into the formula, we get RS equals 1 minus 6 times 27.5 over 8 times 63. This simplifies to 1 minus 165 over 5 out of 4, which gives us approximately positive 0.672. This is a stark difference from my initial incorrect calculation, highlighting the importance of precision. For part B, describing the correlation, we must reconcile our two coefficients. Pearson's RP was 0.749, and Spearman's RAS is now plus 0.673. The discrepancy tells us that a linear model isn't the best fit for this data, and we should trust the rank correlation more. However, a Spearman's RS of plus 0.673 indicates a moderate positive monotonic trend in the ranks. This means that as it takes longer to make a crane, students tend to make more cranes, which contradicts our logical expectation. This could indicate other factors at play, like efficiency improving with practice, or some students simply being faster and more prolific. Our final practice question is a conceptual one, drawn from exercise 7G, question 76. Let's first clarify the terms independent variable and dependent variable. The independent variable is the one that is changed or controlled, while the dependent variable is the one that is observed or measured. For part A, the longest jump is the independent variable. The athlete's performance in the jump determines their placing. An athlete doesn't choose their placing. Their jump length dictates it. So, placing is dependent on the longest jump. Now for part B. Why must the Spearman's correlation coefficient between longest jump and placing be exactly 1? Let's list the jumps from the original data and assign ranks. For simplicity, we'll assign the highest jump a placing rank of 1. Athlete B had the longest jump of 5.29 meters, so they are ranked first. Athlete E had the next longest at 5.22 meters, so they are ranked second. Athlete I had the shortest jump of 3.89 meters, so they are ranked 10th. The ranking for placing is simply the reverse of the ranking for jump length. If we were to calculate the Spearman's rank correlation coefficient between the rank of jump and placing rank, we would find it to be exactly 1. This is because the ranks are identical. The question is about longest jump and placing. Let's rethink this using the common convention that placing is ranked first for the lowest value. Let's assume a placing of 1 means the shortest jump, 2 means the second shortest, and so on. With this convention, the athlete with the longest jump gets placing 1, and the athlete with the shortest jump gets placing 10. Now, let's look at the ranks of the jump lengths. The longest jump, 5.29 m, has a rank of 1. Its corresponding placing is also 1. The shortest jump, 3.89 m, has a rank of 10. Its placing is also 10. In this scenario, the ranks are perfectly matched, leading to an RS of plus 1. This demonstrates a perfect positive correlation. For an RS of 1, we would need a perfectly inverse relationship. This would happen if, for example, placing was defined such that first place was for the shortest jump, and 10th place was for the longest jump. In that very specific and unusual scenario, the ranks would be perfectly opposite, and RS would be 1. Let's work through one more detailed example to ensure you are comfortable with the process. A group of 10 students took a math test and an art test. We want to determine if there is a monotonic relationship between their scores. This is Review Set 7B, Question 4, but we will focus on RS. Here is our data. Let's start by calculating RS. The first step is to rank the data. We have ties in the art scores, which we must handle carefully. For the math test, the scores are already sorted, so the ranks are 1 through 10. For the art project, let's look at the ties. The score 71 appears twice. These would have been ranks 4 and 5, so they both get the average, which is 4.5. The score 82 also appears twice. These would have been ranks 8 and 9, so they both get the average, which is 8.5. Now we calculate D and D. We subtract rank A from rank M for each student. For the first student, D is 1 minus 10, which is 9, and D2 is 8.1. For the second student, D is 2 minus 8.5, which is 6.5, and D2 is 42.25. We continue this for all 10 students and find the sum of all the D2 values. SD2 is 319. My sum of D2 is 319, which is slightly different from the solution. This is common with ties or when using a calculator versus manual computation with formulas. For IB, it's safer to use your GDC. Let's use the GDC to calculate Spearman's rho directly. If you input the math and art scores into your calculator and compute the Spearman's rank correlation coefficient, you will get a value of approximately negative 0.707. The coefficient of 0.707 indicates a strong negative monotonic relationship. This means that, in general, students who scored higher on the math test tended to score lower on the art project. While not a perfect inverse, the trend is quite pronounced. This is a good example of how to use RSS to describe a relationship that might not be linear, or in this case, has a negative association. Let's quickly review the key takeaways for Spearman's rank correlation coefficient. First, our RCS measures the strength and direction of a monotonic relationship. Second, it is calculated by finding Pearson's Ostra R+ of the ranks of the data, not the raw data values. Third, it is robust to outliers, meaning it's less affected by extreme values than Pearson's coefficient. And fourth, you should always inspect the scatter diagram to determine if a monotonic relationship is present before using R**. Understanding when to use Spearman's RCS versus Pearson's RP is a key skill for IB students. It allows you to analyze and describe bivariate data more accurately and powerfully. We have now covered how to assign ranks, how to use the formula and your GDC to calculate Spearman's coefficient, and how to interpret its value. We also tackled the important case of ties and saw how IR stars can be more appropriate than RBAS for nonlinear data and data with outliers. Thank you for watching this lesson. If you're looking for expert tuition and personalized support in IB, A-Level, or IGCSE, please contact DAR Tutors. We're here to help you succeed. You can find our contact information on the screen. We look forward to working with you. Finally, here is a collection of IB-style practice questions for you to work through on your own. Remember to show your work and interpret your results. Question 1 deals with water bills and electricity bills. Think about whether these are likely to be correlated and what the relationship might be. Question 2 provides a Pearson's correlation coefficient. Use it to calculate and interpret the coefficient of determination, R². This is a good review of a related concept. Question 3 is another matching exercise, but this time it includes an outlier. Consider how that outlier will affect the Spearman's coefficient. Question 4 asks you to analyze a dataset with ties, just like the one we worked through. Practice assigning the average ranks carefully. Question 5 is a classic outlier problem. The key here is to calculate RP and RS with and without the outlier and observe the difference. You can pause the video here to work on these questions. Solutions will follow in the next scenes. Welcome to DAR Tutors for online and home tuition. In this video, we will review the worked solutions for the IB-style practice questions we presented at the end of our lesson on Spearman's rank correlation. It is crucial to have attempted these questions yourself before watching this solution video. This is the best way to consolidate your understanding and identify any areas where you might need further practice. Let's begin. Our first question was about the relationship between water bills and electricity bills. The question asks if the correlation is likely to be positive or negative, and whether a causal relationship exists. There is a reasonable argument for a positive correlation. Generally, larger houses tend to have higher electricity bills for heating, cooling, and lighting. They are also likely to have more people living in them, which would lead to higher water usage for bathing, laundry, and gardening. Both variables are influenced by the size of the household and the house, so a positive correlation is plausible. So we can say that a positive correlation is likely. Now, about causality. A causal relationship means that one event is the result of the occurrence of the other. Does your water bill directly cause your electricity bill or vice versa? No, it does not. A high water bill does not cause a high electricity bill, nor does a high electricity bill cause a high water bill. Instead, there is likely a confounding variable, such as the size of the household or the size of the house itself. This third variable influences both the water bill and the electricity bill, creating an observed correlation without a direct causal link. Question 2 provides a Pearson's product moment correlation coefficient and asks us to interpret it and calculate the coefficient of determination. We are given that Pearson's RP is 787 between fat content and energy in food. The coefficient RP equals 0.787 is positive and relatively close to 1. This indicates a strong positive linear relationship. We can describe the relationship by saying there is a strong, positive, linear association between the fat content of foods and their energy content. In simpler terms, foods with more fat tend to have more energy, and this relationship is approximately a straight line. For part B, we need to calculate the coefficient of determination, r squared. The coefficient of determination, r squared, is found by squaring the correlation coefficient. So r squared equals 0.787 squared, which is approximately 0.619. Now, we must interpret this value. The coefficient of determination tells us the proportion of the variation in the dependent variable that can be explained by the independent variable. In this case, energy is the dependent variable. An r squared value of 0.619 means that approximately 61.9% of the variation in the energy content of these foods can be explained by the variation in their fat content. This is a substantial proportion, but it also tells us that the remaining 38.1% of the variation in energy is due to other factors not measured, such as protein content or carbohydrate content. Question 3 is a matching question involving scatter diagrams and Spearman's correlation coefficient. We need to match the three diagrams to the coefficients Rs to 1, Rs il 4, and Rs is 0.7. Let's analyze each diagram. Remember that Rs measures the strength and direction of a monotonic relationship. Diagram A shows a perfectly straight increasing line. This is the definition of a perfect positive monotonic relationship, so Rs for this diagram must be exactly +1. Diagram C shows a general increasing trend, but the points are quite scattered. This suggests a positive but moderate to weak monotonic relationship. An Rs of 0.7 fits this description well. That leaves us with diagram B and the coefficient Rs equals 4. Does this make sense? Diagram B has a negative general trend, so the correlation should be negative. The presence of an obvious outlier is likely weakening the perceived correlation. Without the outlier, the rest of the data might have a much stronger negative correlation. An Rs of 0.4 represents a negative but weak to moderate monotonic relationship. This matches diagram B. So the correct matches are A to A, B to B, and C to C. Question 4 asks for a full correlation analysis of music festival data, including a comparison of Pearson's and Spearman's coefficients. The data shows ticket sales and beverage sales over 12 days. It's logical to expect that on days with higher ticket sales, there will also be more people at the festival, and thus more beverage sales. So we expect a positive correlation. First, the scatter diagram. It shows a general upward trend, but the points are quite spread out. There doesn't appear to be a perfectly linear relationship, which might suggest that Rs will be a better measure. Using a GDC, we find that Pearson's product moment correlation coefficient, RIP, is approximately 0.65. This is a moderate positive linear correlation. Next, we find the ranks for X and Y. Be sure to handle ties correctly. For X, 25 appears twice. For Y, 4, 7, and 8 all appear twice. Here's the table with the ranks. For X to 25, the values would have been ranks 9 and 10. They get an average rank of 9.5. For Y4, the ranks 1 and 2 become 1.5. For Y7, the ranks 4 and 5 become 4.5. For YE, the ranks 6 and 7 become 6.5. Now we draw a scatter diagram of these ranks. It also shows a positive trend, and it appears the points are slightly more clustered than the original data. Using a GDC to calculate Spearman's Rs on these ranks, we get a value of approximately 0.706. This is higher than our RRP value of 0.65. For the description, based on Rs being 0.706, we can state there is a strong, positive monotonic association between ticket sales and beverage sales. The higher Rs value suggests that this nonlinear measure provides a more accurate description of the underlying trend than the Pearson coefficient. Question 5 is another detailed outlier analysis, similar to the one we did in the lesson. We have 13 data points on temperature and customer numbers at a garden center. Let's first plot the data and identify the outlier. The scatter diagram shows a clear outlier. The point, 31, 35, is well outside the general cluster of points, which show a positive trend. We will now calculate RP and RS both with and without this outlier to see how it impacts the correlation. First, with all 13 data points, we find RP is approximately 0.449 and RS is approximately 0.70. Now, we remove the outlier, 31, 35, and calculate the coefficients for the remaining 12 data points. After removing the outlier, the correlation coefficients increase significantly. RP jumps to 0.900 and RS jumps to 0.941. To describe the effect, we compare the two sets of values. Pearson's RAP was much more affected by the outlier, increasing from 0.449 to 0.900. Spearman's RS also increased, but by a smaller margin from 0.701 to 0.941. This confirms our earlier observation that Pearson's coefficient is very sensitive to outliers, while Spearman's coefficient is more robust. This example reinforces the idea that when analyzing data, especially if outliers are suspected, it is good practice to calculate both coefficients and to always plot the data first. Thank you for completing these practice questions with us. We hope this review has solidified your understanding of Spearman's rank correlation coefficient and its application in IB mathematics. Remember the key principles. Plot your data, consider the linearity of the relationship, handle ties carefully, and choose the most appropriate coefficient for the situation. If you found this lesson helpful and are looking for more personalized guidance, please don't hesitate to contact our tutors. We provide expert online and home tuition in IB A-Level and IGCSE curricula. Visit our website or email us to learn more about how we can support your academic journey. Thank you for your time, and good luck with your studies.